Good afternoon, everyone. Today we have the great pleasure to welcome Professor Martín Cismondi. Professor Cismondi obtained his degree in chemical engineering at the Universidad Nacional de Córdoba at Argentina, and he obtained his PhD at the Universidad Nacional del Sur, also at Argentina. He currently works as independent researcher at the CONICET, Consejo Nacional de Investigaciones Científicas, and as associate professor at the Universidad Nacional de Córdoba, UNC. His main research interests are phase behavior of complex fluids and their modeling using equation of state, especially for applications concerning hydrocarbon production, asphaltenes and paraffins precipitation, and PVT behaviors of reservoir fluids as well. Professor Cismondi has over 46 publications between international journals and conference papers, which to date have been cited more than 600 times. So welcome, Professor Cismondi. Thank you so much for being here. Please feel free to start your talk.
Well, thank you, Yuri, for the nice presentation. And let's see, should I share again?
Yes.
No, here. Yeah. Now you see the presentation more. Good.
Yeah, nice.
Well, thank you. First of all, I would like to thank Fred and I mean all the team in the organization, not only for inviting me, but also for organizing and bringing this to reality, because you had not only a great idea, but you make it real week by week. And I think this has been very important in these pandemic times for the thermal community, and especially for students having access to so many great speakers as you organize. So congratulations. And it's, of course, an honor and a big pleasure for me to be here. So as you can see, I'm going to talk about phase envelopes of different types. But first of all, let me tell you, let me tell you briefly why I chose this topic that maybe I could not choose for a talk in a conference, for example, or I would do it in a different way. First of all, recently I realized that certain types of envelopes are not properly understood or even known for many people, even working in related subjects or applications. So this was the first motivation. Then, as many of you know, I really like phase diagrams. I mean, it's my favorite part when teaching thermodynamics, for example. And also, I thought this postgraduate ambient of the atom seminars seemed appropriate to discuss a topic like this. But besides that, it is also related to some of my recent or present research works. So this combination of reasons, I think, was enough to choose this topic among other options I had originally when Fred invited me. So let's start from the simplest of the simple that I guess most of you are very clear about this. This is the saturation pressure curve for pure methane. You know, it separates the liquid state from conditions in which the fluid will be stable as a gas phase. We have the critical point up here. And then if we go to a mixture, you know, we have this phase envelope instead of the simple vapor pressure curve. And we have bubble points up here, dew points down here, and the liquid gas separation inside the phase envelope. I guess you are all familiar with this. The phase envelopes like that, you know, they are also used, for example, for classifying hydrocarbon reservoir fluids, like in this figure from the Pedersen's book. So you can see natural gas to black oil, and including gas condensates or near critical or volatile oil fluids. They can, I mean, the phase envelopes will vary a lot in extension, in the shape, but they are all qualitatively of the same type, right? But what if you get something like this? And this is when the poll comes, and this is important to see the feeling of the audience. I would like to ask you, let's see if I can get rid of this. Yeah. But I need to start the poll, so how should I? Here, polls. So I want to ask you, which of the following propositions represents your understanding or belief regarding this type of strange envelope? Proposition A is, this envelope is not physically sound. It must be an artifact generated from some wrong model, maybe. If you think like that, that is proposition A. Then proposition B is saying the problem is not necessarily in the model, but in the calculation algorithm that was not able to find the bubble pressures at low temperature and diverge towards infinite pressure. Proposition C is saying there is nothing wrong with this type of envelope, which is the correct type for certain fluids. It can be obtained both experimentally and from calculations based on equations of state. And finally, proposition D, this behavior has been observed experimentally for some fluids, but cannot be obtained from equations of state. So, summarizing more schematically, we have the options like this. According to proposition A, it doesn't exist experimentally, but you can get it from modeling. Proposition B is saying it doesn't exist either in experiments or modeling. Proposition C is the opposite, everything is okay. And proposition D, you can get it in the lab, but not from modeling. So I'm seeing the numbers.
How about E? We have
there
an
is no option E. This time there is no option E. I hope no one choose option E, because that would not make sense. But so far, we have all type of options from A to D. So I'm totalizing a little bit more than 30, 36. I think I saw like 60 or more than 60 participants. So a few seconds more. So you make your try. If you are not sure, it doesn't matter. This is to get an impression of what the audience may think. So we already have 40 votes. I think that's enough. So, end polling, and we'll see the results. It is interesting that most people, 60% chose option C, which is the right answer, because clearly, and many of you must know, you can measure these envelopes in the lab, and indeed, you have done that in the atoms group, and I'm going to cite a recent interesting paper from you, from my friend Papa and co-worker, Anna, Fred, and so on. And you can also calculate these envelopes. So C is the right answer. But still we have some people choosing options A, B, and especially D. So I think this is representative of some situations when I encounter people being surprised by this envelope, thinking that there was something wrong, you shouldn't get this, and when actually there's nothing wrong. So this was, as I told you, the motivation. Even for those of you who are already clear about this, I hope I can contribute with some complementary observations, analysis with this talk in relation to phase envelopes. Not only this one, but also some other a bit more complex, but related to this one. So, I can go on. Yeah. So once we accept that there's nothing wrong with this phase envelope, some questions that may arise, I think, are the following. First of all, what does it mean? So what is the physical interpretation of such envelope? Then what type of fluids or compositions may show this type of envelope? Can they be of some practical relevance in reservoir fluids, for example? Also in other type of applications, but I'm more concerned with reservoir fluids, so my examples will be especially related to that subject. And finally, is there any connection between both types of phase envelopes? I mean, the classic one and this open envelope. And in that case, how are the transitions from one type to the other? So the rest of the seminar will be dedicated to try to contribute and to share some light on these issues. Yeah. So first of all, about the physical interpretation, I could summarize in these few words. It's this type of envelope is showing us a gradual transition from vapor-liquid equilibrium to liquid-liquid equilibrium. If you have any type of problem to accept that or to assimilate this idea, I propose you consider the following. If we go back to this simple diagram for pure compounds, you know that you can transform the properties of a gas state like this into a liquid-like state going through the supercritical region, right? That was very clear since the times of van der Waals at least. Also, if we have a mixture phase envelope like this, we can do the same, going from gas properties to liquid properties without any phase transition, right? Again, by surrounding the critical point and the critical region. So what we have in the phase envelope is a transition now not for a stable phase, a monophasic system, but in a saturated system when what is changing gradually is the incipient phase, right? And to go deeper and to analyze now the transition and to show you that gradual transition from another point of view, let's consider this diagram for a mixture when we have, in principle, the closed envelope, but in addition, we have at lower temperatures this liquid-liquid saturation line. So we have LLE below that temperature. We have bubble points at any point on this line, and we have LLE saturation points here. And when both lines meet, we have both points at the same time. That is what we can call a double saturation point, and I will go back to that concept later. So this is clearly not a gradual transition. This is a discrete or abrupt transition. But when we have this type of envelope, it's clear we have bubble points here in this region. It is also clear we have liquid-liquid equilibrium saturation points like here. But what in between? You cannot tell what exactly is the point because there is not one point like here where you change from bubble point to LLE point. So there is a gradual transition here, right? So from this, we start to see the connection between how this open phase envelope comes from this different phase envelope once due to composition changes, these two lines, the bubble point line and the LLE line, merge into one, and we have this new behavior like the open envelope, right? So for simplicity, we will call closed envelope this one and open envelope this one. It is interesting to see that in binary systems, both of them are present in the same system for different compositions, as you can see here in this 3D plot in pressure, temperature, and composition. This example is for CO2 with hexadecane. So there are different envelopes which are closed here, like the first example before, with the separated liquid-liquid saturation line here. That is for CO2 mole fractions below 0.80, and above 80, we have this, you can recognize here, the open envelopes. This is the same, but a capture with a different angle, so we can see better how the critical line in black is surrounding all the envelopes. And again, we have the closed ones here, the open ones here. I tell you briefly, for those who don't know, I generated these plots and some other previous ones using my software JPEG, that if you don't know it and you're interested, you can download it from this site. I will include it again at the end if you're interested. So, coming back, now that we are understanding better what this envelope means and how it can be connected to the closed one, so what types of fluids may show this type of envelope? From the knowledge on binary systems, as I just showed you, we know they are associated to phase behavior of type 3, that is in the classification of Scott and Van Condenenburg. So this is a pressure temperature projection of this type of phase behavior. This is the critical line that we were watching before in the 3D plot. And this is the temperature composition projection. And it is in this intermediate composition region, in between the blue lines mean the liquid phase composition along the three-phase line for the binary system, so the liquid-liquid vapor line. So in this intermediate composition range, where we don't touch any phase at the three-phase line, is where we have these open envelopes. But so far, I didn't mention an example besides CO2 hexadecane, but more cases. Where do we see this in reality? I mean, and water hydrocarbons are known to show type 3 phase behavior. Also CO2 with heavy hydrocarbons, and this is more studied recently in Brazil, indeed, because of the pre-salt, high CO2 contents, and so on. And as I mentioned, I know a nice recent work in the atoms group. And you can also get type 3 phase behavior if you mix polar compounds with hydrocarbons, in many cases. But it is important to remark that even alkane mixture can form or can give phase behavior of type 3 if they are asymmetric enough. As an example, you can see here from one of our recent papers, these are phase envelopes for different methane eicosane mixtures. So this is C20 for different compositions, and you see that for the highest levels of methane, they give open phase envelopes, and this corresponds clearly to type 3 phase behavior. The same with different compositions and both experimental measurements and modeling. This is for C1, C30, so triacontain. No, sorry, triacontain. C30 with methane. And then if we go to related ternary systems, we're going to see the same. In this example, C1, C3, and C24. So methane, propane, and tetracosane for different compositions. We also get these open envelopes. You have the details in this publication if you're interested. Another ternary system, in this case, methane with C24 and C30, the same for different compositions between these compounds. And we always need high levels of methane of around 80% in these cases, maybe 80 to 90, to get these open envelopes. But maybe you are interested in reservoir fluids, so the question comes now, what about reservoir fluids? What type of them could present open envelopes, or which composition ranges could favor them? Because if you remember this figure, all of them are closed envelopes. So is it possible that a reservoir fluid would show the open envelope? So to study more systematically that possibility, we studied this work with Gerardo Pisoni, that I will show some results now. So we had the idea of mapping different possible compositions, and for mapping it's simpler if you do it for a ternary system. So if you try to mimic the complexity of very multi-component fluids, but with characteristic compounds. First of all, methane, which represents the most volatile part of the reservoir fluids, and you know every reservoir fluid from natural gas to black oils, they always have important quantities of methane. Then C8, which can represent gasolines, what we are interested to get in the refinery. And then, for example, C36 for the most heavy part. In this map, we would have black oil type fluids here, high contents of the heavy part and low contents of methane. If we have more methane, we go to volatile oils. More methane, then we would be in the gas condensate region. And then we have natural gas here. This part down here below natural gas, I would call it maybe the non-existent reservoir fluid, because you don't find reservoir fluids which approach the binary between methane and the heaviest fractions without having important quantities of the intermediate. That's why we have this empty part here. So Gerardo prepared an automatized way of running many envelopes for different compositions and automatically detects whether the envelope is closed or open. So here we have the results after choosing, in this case, the RKPR equation of state with correlations of parameters we had from this recent work in our group. So the results we have here, every red point means a closed envelope, and every black point means an open envelope. So you see that the open envelopes do exist in these combinations, and they are found in this region in between gas condensates, natural gas, and what I mentioned as the non-existent reservoir fluid. And maybe that's one of the reasons why they are difficult. They can be encountered, but they're difficult to find. But there are examples, as I will show you in a few slides. But before, let's interpret this evolution what does it mean to change from this red region to the black region? Let's consider, for example, this series of points, each of them having a fixed ratio of C8 to C36, in this case for 1.25, 1 and 0.85. So physically, you can interpret this that like you have originally a fixed relationship between C8 and C36, and then you inject, let's say, more and more methane. So the methane mole fraction is increasing, but you keep the ratio between the heavy ones. So this is telling us that at some point we will change from closed envelopes to open envelopes. And this is what we see here, this nice 3D plot that Gerardo prepared. And we can identify the first one here, the lower methane contents as black oil type, then volatile oil type, and then gas condensate type when we reach to the possibility of open phase envelopes. You see, only for 80% of methane or higher, we get here these open envelopes, but before we had the red closed envelopes. And this is in connection, this is confirming some single results we had previously, like this one for a gas condensate, a synthetic gas condensate mixture, that even though the measurements were at higher temperatures, as usually happens, but when you model this, predictions with two different equations of state were showing these open envelopes with the liquid-liquid branch at lower temperatures. But we had another example, in this case, for a real gas condensate from China. Here you have the details of the publication. This is 87 the mole fraction of CO2, so quite high. So it's approaching the natural gas, but it has still an important quantity of heavy fraction. So it behaves like a gas condensate. And when you see, I mean, not only the modeling, but also the trend in these measurements are showing a clear possibility of open phase envelope. So it can happen. It's not that frequent, but it can happen in reservoir fluids. Now, what about the effect of CO2 and aromatics? So for studying these effects, we found this nice recent work that I was telling you in advance on the atoms group. They did great measurements for different combinations between methane, hexadecane, CO2, and even phenanthrene. So, and then they adjusted the Penn-Robinson to best capture, I mean, this measurement. So we took their parameters to do a mapping similar to the one I was showing. So here, we see something similar to the map before, but in this case we have methane here on the left corner, hexadecane here, and CO2 to the right. You can see here that we have a clearly larger region than before for open envelopes, and this is a consequence of CO2 promoting these open envelopes when mixing with heavy hydrocarbons, like in this case C16. Similar to before, if we choose this series of fixed relations, in this case between the two alkanes, and then we add CO2, we would move forward in this direction. And what is interesting to see here is this phenomenon that, I mean, in most part of the map, we go from the red region to entering the black region when we increase the CO2 content. But there is this specific ratios when we can go from open to closed and then to open again. That was quite particular and interesting. And that implies the following. We have, for low CO2 contents, these open phase envelopes. Then it closed, in the case of the red ones, contents from 0.30 to 0.60. And then for 70, 80, and 90%, we are back to open phase envelopes. And this can be surprising, and you can ask yourself what happened with the liquid-liquid separation in these envelopes in between, the red ones. We have a different capture here in 3D, which is maybe clear to see this evolution. So what happened with the liquid-liquid separation that clearly is present here and here? What happened with the compositions in between? If you search for that liquid-liquid line, but the details are beyond the scope of this talk, but it can be done, and you would find this liquid-liquid line that is normally not obtained in standard phase envelope calculation algorithms. But you would get this crossing in this example for the 60% CO2 case. So this means that there is also the liquid-liquid equilibrium region in this case, but it is not gradually connected to the vapor-liquid part through a gradual transition, as I explained before, like in the other cases. And here I should remark that these segments here are unstable. The ones below, let's say, the double saturation point. Yeah, so this is a double saturation point, like I had explained before, and the segments below are unstable. But you can detect that only by running the two segments or by doing stability analysis here. Then we go to add phenanthren, and now we have 4 components. So what we did here in order to map in a pseudo-ternary form, so we grouped C16 and phenanthren here in the upper corner, and we still have methane here and CO2. There is some evolution of the ratio between the two heavy ones, which in this case is equal to the ratio between methane and C16. It could be done in a different way, but this is the evolution that we follow here. But the important thing to show here is that the black region, so the open envelope region, increased a lot compared to the one before. And this is a consequence of phenanthren, the aromatic compound, promoting again the open envelope. And this is because there is more immiscibility when you tendency to liquid immiscibility when you have aromatic compounds with CO2. And again, we have, if we choose the right ratio between the hydrocarbons, we will have this evolution with closed envelopes in red for intermediate compositions, where you have open envelopes for larger and also for lower CO2 contents. This is the corresponding 3D plot. This is an interesting phenomenon that we found only after mapping all these possibilities. So some partial conclusions so far is that high contents of methane and or CO2 combined with low quantities of heavy compounds are likely to present open envelopes. aromaticity in the heavy fractions also increases the chances. And some other comments or observations I would like to make is that open envelopes might be not so infrequent in reservoir fluids, but they are difficult to confirm experimentally due to the following reasons. Different reasons, and I would choose mainly the following. First of all, as I showed, they appear, I mean, the liquid-liquid separation part appears at lower temperatures, normally lower than 300 Kelvin, and there are not many experimental studies going to that low temperature range. Second, for some paraffinic fluids, wax may precipitate before you can reach the LLE point, which is the vertical part of the open envelope. And even if it's not like that, and you could in principle measure the liquid-liquid saturation point, it is difficult to observe or detect LLE saturation points in comparison to BLE. I think the experimentalists here can agree on that. And especially in reservoir fluids, in petroleum-like fluids, because of the darkness. So, and you know, you have to resort to different experimental techniques to detect those points, which are not easy. So sometimes you may think you have only one liquid phase, but actually you have two, but it's difficult to detect. And these last observations take us to this last part of the talk, because there is a type of system which is liquid-liquid, but which can appear at slightly higher temperatures, which is of practical interest. There are complex techniques to detect those points, and this is asphaltenes, of course. This is a publication I made a few years ago, and I think it's very much related to these envelopes we were discussing, so that's why I chose to show you this. That in cases like this with asphaltenes, if you start the calculation of the envelope from the low pressure dew point side, like this, you will get the envelope in blue. This is clearly an open envelope. But if you start from the low temperature bubble point side, like this, you will get this another one in black, which has clearly something wrong or something surprising here. This shape is always related to instability. So when you have this, the external segments will be stable, but then in order to complete the stable predicted phase diagram, you have to discard the unstable internal segments. So we go from this to this once we discarded the unstable segments, and from this double saturation points, we have the information to start the calculation of these three-phase border lines and complete this type of diagram. If we focus on this region of interest, we have the double saturation point here. In this case, coming from the oil stable region, in these points on the black line, a bubble of gas would appear, so that's a bubble point. And here on the blue line, the asphaltenic phase, the first droplet of the asphaltenic phase would be formed. But in this case, this is called double saturation point because you have both incipient phases at the same time. And that is why also how you can move from one phase region into three-phase region when you enter here through the double saturation point. Then you have oil plus asphalt in here, two-phase region, and oil plus vapor, two-phase region here. Then in that paper, I also considered another case quite similar to the previous one, with some experimental points here. Quite similar, except for this part in the higher temperature region. But then this is very interesting because this case is really different to the previous one. And in this case, the whole open envelope, this one, is stable completely. And you can get the other envelope if you start calculating from the bubble point side from low temperature. You can get some other envelope, but completely unstable, and that is why it is not included in this figure. Then we have these other 3 phase region envelopes. So there is no double saturation point in this here because there is no crossing between segments. So we go from 1 phase here, 2 phases, 3 phases here, and then again to 2 phases. All the details are in that paper in Energy and Fuels. So now completing the conclusions, and I mean the take-home message I want to put here is that be careful, because after calculating a phase envelope with standard algorithms, either it is your own algorithm or commercial software package, some people may think, oh, it looks perfect when you get something like this, so they feel like this, everything looks right. But when they get something like this, many people used to think, oh, something must be wrong. So they felt like this, and sometimes even like this. But actually, from all the explanations and what I was discussing, if you get this open envelope, it will most likely be the stable phase envelope, unless there are crossings with the false bubble pressure line, like I showed in the example before. So I recommend to check that. And if you get this closed envelope, be careful, because sometimes, depending on the compositions, a liquid equilibrium branch could be missing at lower temperatures. Or maybe it could be partially or completely unstable, as I showed for asphaltene cases, and it can happen something equivalent for cases with water or with other polar compounds. So don't feel like this so easily when you get a closed envelope, and no need to be scared if you get an open loop. And I think to keep thinking on this most of the time, not to say always, it's a good thing. Now let me briefly thank to my co-authors and collaborators in some publications and mentioned and the present work. This is Natalia Tassin. She defended her PhD thesis like 1 year ago. Belen Rodriguez was her co-supervisor. Vanessa Macietti, who before going to Atoms, she was working with me and is co-author of one of the publications I mentioned. And maybe I will have the opportunity to co-supervise her PhD, thanks to the invitation of my friend Papa. And of course, Gerardo Pisoni, who was preparing many of the plots I've shown in this talk. And now let me tell you, I guess most of you are familiar with this historical and famous expression attributed to Newton, but it came from before. And I could say, of course, more modestly, but maybe I could say that if I developed GPEC and it was useful to many people, and maybe, hopefully, if I could contribute with some explanations in this talk to clarify about phase envelopes, it was by standing on the shoulders of these 2 giants to whom I will be thankful forever. Esteban Brignole was my supervisor for my PhD, and he introduced me to the study and to the passion about this high pressure phase behavior. And And then in Denmark with Mikkel Mikkelsen, I mean, I learned from him the specialized numerical methods that allow you to track all these complex envelopes and critical lines and so on that can go through different minima and maxima and different variables. Most of you know that Mikkel passed away last year. That was a terrible, sad loss, but it's clear his legacy continues with us. We remember, for example, this picture of him in Córdova in 2009 when he visited us. And so I will be thankful forever with Mikkel and with Esteban, who are very deeply related to the subjects I discussed today. And as life just flows and goes on, let me briefly tell you that I'm enthusiastic and happy that this new generation is coming. These students who started to work with me, Julieta, Agostina, and Oscar, they already got their PhD grants from CONICET. And Mariano and Federico, we hope they will soon get theirs too. So with that, and happy also for having as co-supervisor for them again, Belen, who is a pleasure to work with her, Miriam Strumia, who is the director of our institute and has a lot of experience in the lab and with chemistry, and Gerardo Pisoni, as I already showed. So thank you very much for your attention. I hope it was not so long talk.
Thank you, Professor Cismondi. We are now open for questions. If you want to ask one, please enable your microphone. You can also write it on the chat and we'll read it. And of course, our YouTube viewers can also ask questions by writing on the chat.
So I would like to make one question. Can I go on, Yuri?
Of course, of course.
Okay. Hi, Professor Martin. I'm Maria.
Hi.
Thank you for your nice presentation. So I work with multi-component mixture from the pre-salt field. And I observed that when changing the binary interaction parameters in my simulations, the phase envelope went from closed one to an open one. So I would like to ask you, how can the binary interaction parameters affect a phase envelope in a simulation?
Good question, Maria. And happily, I think I have just here I had this just in case, which is related to this type of fluids and to the work I mentioned in the atoms group. And this is a good example of how binary interactions parameters can affect the behavior. Because this is the binary CO2 hexadecane. I mean, this is the binary, but it goes the same way for multi-component fluids. The effects are very similar, but it's easier to show it this way in binary phase diagrams. So we have the diagrams above. These ones are exactly with the parameters that your co-workers at the atoms group adjusted for this case. You can check it on the publication. Is this Kij of 0.0898 and Lij of 0.069. Below, we have the corresponding predictions keeping the same Kij, but without the Lij. So we have a null Lij, which I consider, for different reasons, more appropriate. You can see that the critical line didn't change that much. Of course, there is a change, but it's not that important. But what changes more is the extension, the composition extension of the three-phase line. You see that the blue line is, they are closer above here. This is the predictions we can find from the paper. And this is more open here. And even though, of course, they adjusted the parameters because they got better representation of the phase envelopes they measured, but that made this region of phase envelopes shorter than it should be, because in terms of compositions in this part, this is closer to experimental behavior. Of course, this is not because, I'm not saying they did a bad work in the parameterization. They did a very nice work, but CO2 hexadecane or CO2 alkanes are not easy to model with standard mixing rules, like in this case. So you cannot have everything at once with the same parameters. But what you experience is something very common when working with this type of behavior, with these systems. The behavior and the envelopes, especially conditions, are very sensitive to binary interaction parameters. Yes. Then if you're interested, we can discuss more detailed issues. But of course, it's clearly they are very sensitive to interaction parameters.
Yes, I was working with a multi-component mixture from the episode field, and I don't have experimental results like to adjust. So I was confused. So thank you so much for your presentation. Very
You're
nice.
welcome.
Thank you.
Thank you for your question.
Hi, Martin. This is Charlie from U of A.
Hi, Charlie.
Hi. You should have
Nice to see
presented
you.
your results 6 years back in Palo Alto, and I would have learned a lot from you. So actually, I have a couple of questions, but I would like to start with one comment. Is you said that the binary mixture of C1 and the heavy component may not be applicable, but I think that is very important. Physical phenomena may happen during the WAPEX process, like using the C1 or CO2 as a like a solvent to inject to the heavy oil in Canada during the SEG-D process. So I believe that your work should have a very broad application in that area. So it's a very nice presentation. But I have a couple questions.
Thanks
I
for
will
the
start
comment.
with the first question is about the minimum miscible pressure, and people are interested in CO2 and oil minimum miscible pressure, but I noticed that some of your like liquid phase equilibrium, that kind of coexistence can occur quite high pressure, high temperature conditions. So does it mean that when people try to get the CO2 and the heavy oil MMP becomes meaningless? So that is my first question. My second question, I'm thinking about what's the physical origin of you having this liquid phase separation. I would guess the one liquid phase is the heavy oil component, purely liquid phase. The other one should be the CO2 as a solvent, and the heavy oil is dissolved in CO2 as a solvent. Maybe I'm wrong, but I'm trying to understand what's the physical origin. Maybe is it related to solvation structures and the solvation free energies? So if you can comment on these 2 points, I would really appreciate that.
Well, interesting comments and questions. Starting from the last point, I think you can have different interpretations in terms of, I mean, at the molecular or atomic level about interactions, and you can do molecular simulations to understand better and so on. But the fact is that CO2 and heavy hydrocarbons are not completely miscible in the liquid state. That is very well known. Then you can discuss why and how, what happened at the microscopic level. But it is clear from macroscopic observations from the lab, from the behavior of fluids in different conditions, it's clear they don't mix completely in the liquid state. So that is the reason for this behavior, in a few words. Then about the MMP, of course, the MMP is always, I think, important. It is meaningful, but But in cases like this, and when you have still three-phase behavior at high temperatures, as it can happen, it could be more difficult to get, or I mean, there are more complex behaviors involved, and maybe the standard algorithms to compute MMP that do not apply, and then you should consider somehow these more complex behaviors in a modified algorithm. It depends how you compute, because they are different approaches for simulating and for getting the MMP.
Okay, thank you, Martin. Wish you to have you at Alberta one day.
Okay. Oh, I would love to visit there again.
Yeah, thank you.
Thank you.
We have a question on the chat by Rafael Charin. Do you want to ask, Rafael?
Yeah, it can be. Congratulations, great presentation, Martin.
Thank you.
Did you consider the solid formation in the simulation of the system, methane, CO2, N-hexadecane, and phenanthane? The solid formation, because the N-hexadecane has the temperature of melting like 18 degrees. So it should have a line of solid, maybe before the liquid. So this is some issue in this situation. That's why the paper does not show the low temperatures results, of the simulation.
Okay. Good point. That's an interesting comment. But I mean, and I just mentioned here that one of the reasons that sometimes the liquid part is not found experimentally is because wax can precipitate first, or in these synthetic fluids that would be hexadecane in solid state. So first, the first answer to your question is we didn't consider that in this study, because we are focused on the fluid envelopes. In another study, indeed, in Natalia Tassin's thesis, we computed the solid fluid equilibriums in cases like this, but not for this study that we are focused on the topology, I mean, of the fluid phase envelopes. But what is interesting is that if we go to, for example, with or without phenanthane, for example, this one. Okay, you can say, and that's right, that's a good point, that you don't care, and I accept that you don't care about the liquid line that may appear here, because it's at lower temperatures than the solid phase could start to form. But the case is the same for these parts of the other envelopes. You see, the point is that the standard phase envelope algorithm will get these ones because they are connected to the vapor liquid part, but usually they don't get the other one because the other ones are not connected to the vapor liquid part. That's something I mean, that can be or not of practical interest depending on the case. Yes, but I just wanted to point out, to remark that you should be aware that sometimes when you calculate the closed envelope, then maybe you are missing at lower temperatures the liquid part. In some cases, it will not be of interest, but in some other cases, it can be.
Okay, thank you.
Thank you for the question.
Professor Haya?
Hello.
Hi, Hassan. How are you?
Hello, Martin. How are you? It's a very nice presentation and very important observations you have made, but I just want to add that it's even true in condensate fluids we are measuring. It does has two liquid phases, and the classification which you're talking about, long time ago, our friend Tavares in his master's thesis had in his appendix, type 2, type 3. Now we find when you have many compounds, it's much more complex. You may have even type 8, and we find things systems oscillate. That's the current system between 3 and 4. And I can show some envelope if I can share some screen. I don't know whether I am allowed to share screen. If you said I can show some envelope, the type of even very light fluids, how they can behave. I don't know, Larissa, let me share, but I can show some envelope if you want. The type of envelopes, even very light systems that you have, as you rightly marked.
Yuri? Can
you see this?
Sorry, what?
Professor Haja wants to
share the screen.
Oh, I have to close Professor Martin's screen.
Okay.
Are you okay, Martin?
Sure.
I close
Okay.
your presentation so that Professor Haja can do it. Okay.
The type of systems we are measuring are like this now. Is there light? Can you see the screen?
Not yet.
No.
No?
You're allowed to share now, but you have to click the button and choose which
Oh, it's
screen.
okay.
Yeah,
I can simply tell.
The green one below, share screen. If you see. But in relation to your comment, one thing that is clear is that when you go from binary to multi-component.
See now?
Almost.
Yeah, we see that you are sharing some screen, but I think it's loading still. It's now there it is. Yeah, we can see the diagram in the
Okay, I
Word.
will close that.
Good.
The type of condensate system we are studying is as a light. Can you see this?
Yes.
Okay. This is a reservoir fluid, two liquid phases and a gas phase, and a conditional reservoir is something here. We have a light and a heavy liquid, even with the condensates. This is a big problem. You have a dew point curve, the light liquid curve like that, and basic overall thing is for the heavy liquid phase is an open curve, and we have a dew point curve for a light and heavy fluid like that. So this presents a very complex behavior. If you can see, for example, even without adjusting parameters, it can have two liquid phases at a certain pressure. Then it have one gas phase and two liquid phases at particular pressure. Then single gas, then we don't know what the gas and liquid phases. This is for naphthenic compounds, it's carbon dioxide, high carbon dioxide. So what Martin is telling is very, very important. When you see strain behavior, we don't have to throw it out. It may be real. That's that's the most important point. So maybe your equation of state sometime may not be able to touch it. Luckily, even Peng Robinson 78, if you adjust the parameters, you can show this type of behavior. It may not coincide numerically, but it will show similar behavior. And phase is really complex. Luckily, we have Papa, now we have Sharin with us. So we are trying to cope up with this type of behavior. Thank you, Martin, again emphasizing this type of behaviors. That's all. Thank you.
Thank you, Raja, for the comment. It's very interesting that you show these complementary cases that also show the importance of this type of envelopes. One thing you mentioned about the models, I didn't want to mess with models or algorithmic details in the talk because we had enough with the physical interpretation. This was about the phase diagrams. of course, I was using models and parameters, but that the details of the modeling part could be maybe for another talk. But it's true. Briefly, just to comment on that, I think with cubic equations of state and standard mixing rules, you can model quite well all the hydrocarbons part. Then with CO2, more or less, if you want to cover wide ranges and different behaviors, you need some other mixing rules. And with water, no doubt that for water you need something else, either Uron-Vidal-like or association models. Because as I mentioned, and I think you showed in your picture, Raja, you also had the water dew points that are also complex and can have crossings with the other. And you can calculate that with any model. But to capture the real behavior, you need some more complex mixing rules or association models, right?
Thank you, Martin, for your comments. Only problem with the complex models like PCSAF is it may show behaviors even more complex. We don't know whether it's real or not. The number of roots can be 4, 5, then it becomes even more complicated. That's the problem.
Yeah, that's true. And you have to be careful.
With a simple model like Penn Robinson, we know there are only 3 roots. We can at least calculate something. We can adjust the parameters. That's all. Okay. So we are sticking with the SRK or PR 78.
Okay.
Thanks, Raja.
Thank you.
Richard wants to.
Richard, yes.
Yeah.
Hi, Martin. I always enjoy these talks. And
Richard, can you open your
oh,
camera?
sure, sorry. There we go. So, yeah, I always enjoy these talks and trying to understand these diagrams. I'm still trying to wrap my head around all these different types of diagrams. You had one question about solid-liquid equilibria, and you talk about sometimes you see a phase diagram and you're afraid of it, and so you don't. Like I have results that I never published because I don't know about it, and that relates to some nutraceuticals. So it was curcumin that we were extracting with CO2 and separating and purifying.
Mm-hmm.
You would also probably see this with phenanthrene would be more likely, where the solid liquid equilibria would cut into things. Is it simple enough to just draw a line across your temperatures and say, okay, below that I have solid liquid equilibria, and then whatever hits that line, you just draw a white space just to erase that part of the phase diagram? What do you do?
Okay, interesting point, but it's not so simple, because one thing is the pure compound melting point, but you know, for lower concentrations, you would normally you find at lower temperatures the onset point or the saturation point for the solid phase formation, right? And that and how it changes is not linear, or sometimes it's simple, sometimes it's not linear. So you need to model that, combining an equation of state with some type of model for the fugacity of the solid phase. And from that, there are different approaches for that in the literature that we use either for paraffins or for any type of solid phase formation. So you need to combine the equation of state with something else for the solid fugacity. And from that, you do the same. You adjust some parameters normally to the experimental measurements available, and then you can predict the rest. So the temperature of that solid phase formation is not that easy to anticipate, as you asked.
So is there any, have you written any paper that shows, sort of like the Van Koningberg and Scott, you know, when you have SLE, you know, crossing,
well,
a family of types of diagrams you might see.
Yes. There is, I mean, an equivalent classification, but including the solid phase formation. I think your question goes to that. And there is I think there are different attempts to come with such type of classification. One of the more important ones was that of Yamamoto. I think it was around 1990, more or less, that we cite, and they classified types with letters like A, B, C, D, E, and F. And we refer to those behaviors in another recent publication we have from the thesis of Natalia Dassin. We refer to that classification for those behaviors with binary systems, including the solid part. I would recommend you to have a look at that classification of Yamamoto.
Okay, yeah, that sounds good. Thank you. And then I had another maybe educational question. You know, when you read the original papers of J. Willard Gibbs, he talks about these phase diagrams that they're very clear in his mind, okay, of plotting entropy versus energy and that sort of thing. But I was wondering if does GPEC have that capability to make a pure component phase diagram?
Oh, yes. I think there was a question like that in the chat. I'm not sure if it was you, but if you mean the saturation belt for the pure compound, yes, they are included in GPEC calculations, and you can, there are different plots included in GPEC that you can switch from one to the other. And when you go to the projections having density as one of the variables, you will see the saturation belts for both pure compounds of the binary system. So they are included already.
Okay, I'll have to check that out. Thanks.
Thank you.
Another question? Does anyone want to ask something?
I have a silly question. That comes from engineers, from petroleum engineers normally. I don't think it's important, but even though they want to know if a fluid is a liquid phase or a gas phase at high pressure. So how can we classify, well, it's very easy to say if a liquid phase or gas phase at low pressure, but at the high pressure, sometimes, well, it's hard to say. Or even if you have a liquid-liquid phase equilibrium or a gas-gas-liquid phase equilibrium or gas-liquid phase equilibrium. So, do you have a suggestion how we can still say if a phase is a liquid-like or a gas-like, even at high pressure?
Mm-hmm. That's a good and interesting point, Fred, when you discuss this with different people in real life, industry, and so on. And I know different people have tried to define criteria based on different ideas to put some arbitrary frontier between liquid and gas. But I don't like that because that's clearly arbitrary. My short answer to that question would be that you have to accept that real life is not only gas and liquid. There are intermediate states in between. I mean, we have the supercritical fluid states I think that's clearly understood by everybody for pure compounds. And it's quite similar for mixtures. It's not only gas and liquid. You have dense gases at high pressure that slowly and continuously transform into liquid-like fluids.
Oh, yeah.
That's real life. That's how it is.
Yeah, I wonder if we have some idea, but okay, I think this we agree completely. Another point is you didn't show the solid phase. I understood that you keep in a region of a study, but you didn't show either the dense profile. And some of these phase diagram has some very peculiar dense behavior, and
Yes.
some of liquid may change the density or even cross isodensity situation. So we call here inversion of the dense profile. Right?
Yeah, sometimes called
That's
right?
Yeah. You have a publication about this. I read it a lot already, but you can measure this. It's very interesting behaviors. It's not easy to measure the point, but because kind of it appear like an emotion for some regions. So how to define exactly the point for inversion is not so easy.
Yeah.
But what I'm curious about is it is observed in our lab for CO2 hydrocarbon. But now Total and Petrobras published a paper very recently showing that it may happen with methane and hydrocarbon. So that's very, I didn't expect this. The liquid like, or I don't know, gas liquid, or I don't know how to call, but inversion of density with methane. So it's very surprised for me. It just was published, but did you see this?
That's interesting. I hadn't seen it for methane hydrocarbons, the phase inversion, but somehow it's not that surprising because it's type 3 phase behavior. And barotropy, this phase inversion phenomena, it has been measured and it's known to be associated to many type 3 behaviors. And then it depends on the density of the pure fluid, because we know CO2 is relatively heavy in comparison to hydrocarbons, and that's why, and I mean that's promoting the phase inversion. Maybe you don't expect that for methane, but maybe in some extreme, I don't know what are the conditions, but it could happen. Yeah, that's interesting. I would like to see those results. If it is published, I would like
think
to
it's published already. He told the guy told me that they published already, but I haven't seen the publication. I'm going to get the publication sent to you.
Oh,
I think it's very interesting.
Thank you. Of course. Thank you.
So everyone, since our time is almost up, I want to thank everyone for this discussion. And once again, thank you, Professor Cismondi, for the nice presentation.